Yeah. So I thought I'd share this instead of the slides. I can ask my usual questions. Tell me what you remember from last time.
One-tailed tests are voodoo bullspit.
Yes.
Got it, got it.
Yeah, and
And
why is that?
well, I remember from that that we went into the conversation of variance, and the lowest amount of variance you can have is 0, and it will always be positive because it's squared. So that's the only time that the one test really comes in. But the two-tailed test gives you more of a, like, I guess, more inclusive thought of where we would not have our area of confidence. I don't know if I'm off the mark here.
No, you're on the mark. Does anyone want to help him out? Add to that?
So if I'm remembering right, if our point that we find in the hypothesis test is in the tail or in like outside the curve in the tail,
Mm-hmm.
we it is statistically significant and we keep H naught or maybe we reject it. Never mind. I did not provide any assistance there.
No, you're good. You're good. So what the question is about this tail. So the idea of we expect something to happen, but what we expect is not going to happen exactly as we expect it. There's going to be some variance around it, right? Some inconsistency, some variability. So the idea of one-tailed versus two-tailed is an ahead of time distinction as to whether or not we're going to count something unexpected happening because it was in the too low direction or the too high direction. And so my thesis statement was that one-tailed tests are not appropriate anytime where either side would be a meaningful result. So if you're testing a sample mean against some hypothesized population mean, you could be off in either direction. Therefore, it makes sense to view the total area in which you're willing to be wrong as coming from either side. And so, yes, the terminology then, if you are past the cut point of where you determine that unexpected starts. So that's what we can review today, where how to make that distinction. What you're saying is that X% of the time this would happen if the null hypothesis were true, meaning it's just within expected fluctuation, it's not something discrepant to be worried about. If it happens less than that percent of the time, then we reject the null. We say the result is significant. So if it's sufficiently unexpected, it would happen with a low enough probability that we would say it is unlikely that this sample came from the same population. That's the idea. We don't know where it came from, right? If it's not the null, then what is it is something that we don't tackle. But it's just a question of relative to our expected as the benchmark, where do we fall? Yes, good stuff. What else?
We heard about the story from, I think his name was Gossett,
Yeah.
related to the student's T, as that's where that came from.
Mm-hmm.
Um, and essentially, like, we talked about how for a lot of what we're doing, we'll use T instead of Z.
Yeah. Do you remember why?
Nope.
Okay. I like the honesty.
Is it based on sample sizes?
Yes, it
Like
is.
it has, isn't it 50 or greater to use T or I don't know.
I think that's a rule of thumb. 30 is what I was sort of told, but it depends on your critical value. Fayaz, were you going to say something about that too? Wait. Oh, I can't hear you. Oh, we're having audio difficulty. You can use the chat window too if you want to. Let me pull up some slides so we have a visual to go along with what we're talking about here. Mic is not working. Ah, but your fingers are working, so we're all still good here. Um, Let me go back to this picture right here. Let me move this little thingy out of the way. So this is slide 59 in lecture 1 that I've pulled up here. Z versus T is what we're talking about. So the purpose of T versus Z, they are distributions that are supposed to characterize the variability across samples and what you would get out of any one sample. So we're concerned with the mean right now, but throughout the course, what we're concerned with will change. Later on, we're going to be concerned with the variability in the size of a relationship between two variables, for instance, which would be conveyed as a slope. So this is a more general concept that I'm introducing with the mean, but it goes beyond that. And so the idea of where expected versus unexpected is comes from a distribution. And the difference between Z and T, which is on slide 57 right here, let me go ahead and, yeah, we'll just keep it like that for right now, has to do with sample size. So Z refers to a standard normal distribution. And no matter how many people you have in your sample, it is supposed to hold. And what Gossett, who worked for Guinness Beer, discovered by accident was that it doesn't work when you have very small samples. And it works less and less well the smaller the sample. And so this picture illustrates the differences in the theoretical distribution for Z versus T, where the black line is Z. The blue line is for degrees of freedom equals 6, meaning sample size minus the number of parameters that you had to spend, points you had to spend to know what you're trying to know. So for instance, if you're just trying to talk about the mean, then degrees of freedom equals 6 would go with 7 people. So 7 minus 1 mean is 6. And then 3 would be the red line here. And so the fewer people you get, the flatter the distribution gets. And the consequence of that is where unexpected starts. So these numbers down here, the 1.96, the 2.45, the 3.18, those are what's known as critical values. They are lines in the sand that are used to denote when you hit the magical percentage that you set a priori as to where unexpected starts. So if we set an alpha, that's our percent unexpected of 0.05. What we are saying is that anything that happens less than 5% of the time, we're going to flag as unexpected, significant, reject the null. All of those terms go together. Unexpected, significant, reject the null. And so it takes the flatter and flatter your distribution, the further and further out you have to go to get to where 5% starts. So the standard changes as a function of sample size. And once you get enough people, the standard is the same. And so I tried to make a picture for what enough would be. This is slide 58. And so the different colors indicate different alpha levels. So how certain do you want to be that you found something unexpected? If you want to be extra certain, alpha of 0.01. Less than 1% of the time you would find this if the null hypothesis were true. There's a bigger difference between T and Z as a function of sample size for that level of certainty than for the other ones. And so I'm going to go with maybe teal, aqua, somewhere in there, light blue. That one corresponds to an alpha of 5%. And so at some point, these curves converge, but it doesn't look like that happens until, I don't know, like even at 80, they're still a tiny bit different. Cyan. Okay, yes, thank you. And then green converges faster. So green is for a 10% alpha, which would correspond to 90% confidence. So in practice, you don't really have to worry about this. Most of the time, what you will get is the t value that results from whatever test you're doing. So whatever question that you're asking, you get a t-test statistic that goes along with that question. And then the software automatically calculates the probability that goes with that t. So you don't have to figure out what the critical value is based on your degrees of freedom because it's not really relevant. The software computes an exact p-value. So it's not just an up or down, less than 0.05 or greater than 0.05. You get the exact probability. And so the label is an up or down. So significant is any p-value that is greater than or equal to 0.05. Non-significant, or said that backwards, significant is a p-value that is less than 0.05. Non-significant is a p-value that is greater than or equal to 0.05. Okay, so thoughts or questions on any of that much?
Maybe this is going to sound foolish, but with our experiments we do and stuff, like to push the boundaries of our research forward, don't we want to find things that are unexpected and new? I mean, doesn't it get, I mean, otherwise we're just doing the same thing, which I suppose for some things is cool, but I thought we wanted to find like new, unexpected, statistically significant things. Or am I wrong?
You're not wrong, but I would say it depends on the context. So in some circumstances, you don't want to be different than expected. So as an example of that, if you were trying to claim that a sample of people that you had obtained was representative of the population, and you knew from a larger database what the population average of something was supposed to be, you want your sample to match. And so you would hope for a non-significant difference, meaning, yeah, it's within expected sampling variation. I'm right where I'm supposed to be. But if your test is referring to a relationship between variables and you want to be able to say, yes, these things are related, if you know this, you can predict something else with that, then yeah, you hope for a significant relationship, because what that means is that it's significant relative to an expectation of 0. So the null hypothesis is the key. Null doesn't mean 0. Null means what you think. And I hate to tell you this, but there is a term for when the null hypothesis is not 0. Are you ready for it? It's a non-nil null. I swear to God, that's what it's called, a non-nil null. So you don't always have to test against a 0 as an effect size. So if you're dealing with a body of research that is large, and you already have a decent expectation as to what you should find, say a correlation value of 0.2, indicating that as x goes up, y goes up by a little bit. You could set that as the null and test whether or not what you found, maybe it's a different kind of sample or a different context, and so you're not sure if you should find the same kind of relationship. You could set that as the null, the 0.2 instead of 0. So it depends on your goal. I would say in general, if you're looking to find something, you want it to be significant because you're trying to say that it's found. It's not nothing, but not always. Okay, good. All right, other thoughts, questions? Do you want to go back over any of the stuff that we were looking at last time? Do you want to look through your notes or your slides and see if there's anything that you want to hear again or hear more about? Otherwise, we can keep moving forward. I have an example. Example? Yeah, all right. Okay, so picking up on slide 62 here, summarizing where we've been so far, and then I'll show you a couple examples. There we go, slide 62. So descriptive versus inferential statistics is terminology that I introduced a couple classes ago. If you just want to talk about like the central tendency of your sample, you can compute a mean or a median and call it good, right? There's nothing wrong with that. But if you want to talk about how your sample somehow can be extended or generalized to a broader population of people, then you're talking inferential statistics. And the key to making that translation is to get some kind of index of the expected inconsistency of what you found across samples of the same kind. So all we've learned how to do thus far is to compute a mean and maybe a variance. That's fine because that's enough to get this concept across. So if we have a sample of people, we can compute the mean for a quantitative variable. We can compute the variance, which is an index of dispersion. So it's how far off each observation is from the mean squared, and then divided by n minus 1. If you unsquare that, you get your standard deviation, how far off any one person is from the mean on average. We can feed that standard deviation divided by square root of n. Do you remember what n is?
Is it the population or is it?
It's a sample something.
It's the sample size.
There you go. And welcome back to the microphone. We got the technical difficulties repaired. Yeah, sample size. So standard error then is your standard deviation. You can substitute the one in for your sample if you don't know the population one, which is usually the case, divided by the square root of n. And so,
I have a question.
yeah,
So
sure.
I used to think that small n is the sample size and big N is the population sample size.
I am not familiar with that version of the notation because the population you don't normally know how big it would be. The way that I typically see this is n is the overall sample and little n would be a subgroup. Like if you had a control group and a treatment group, you'd describe their sizes with little n. In the class that happens after this for longitudinal analyses of people measured over time, little n is the number of occasions and big N is the number of people.
Okay,
So
that
yeah,
makes sense.
some kind of n is sample size. I can say that much, but then beyond that, it may be author or context specific. But yeah, sample size. So my point, though, is that once we know how many people we have and we know how variable those people are relative to each other, then we have our standard error. And so standard error is not a people idea, it is a sample idea. Standard error is how far off on average a sample statistic is from the population parameter that it's trying to approximate. So it's the expected discrepancy or inconsistency across samples. And given this formula, we know that you would expect more differences across samples in samples that have people who are more discrepant and in samples that are smaller. So inconsistency is higher if you have more variability and a lower sample size. And we use the standard error in a couple different ways, although they're very much related to each other. One is to compute what's known as a confidence interval, which is the range in which the population version of the parameter is predicted to fall X% of the time, where X is your confidence level. So you can talk about, say, a 95% confidence level, which translates into a 5% alpha level. So the two terms are inversely related. And you can then put the standard error in this part here. So the mean would go where estimate is, plus or minus T critical. That comes from where the dividing line is for where significant starts and non-significant is in the middle, and make your confidence interval. You can also use the standard error here in your what's known as a t-test or a z-test. And so this is our first example of a test statistic. And so the formula you'll see is exactly the same. The result of taking the sample mean minus the population mean and dividing by the standard error is the purpose of that is to create a standardized metric where 0 is whatever you expect to be, and the standard deviation for how far off you are from where you're expected is determined by your standard error. And so how we then use this to determine our significance level is whether we're basing this on a t distribution or a z distribution. And most of the time it's going to be t. So when would we do this in practice? Well, I have a paper that I was like 6th author on or something, of a large group of folks that I did all the analyses for. It was published in 2018, so the lead author is Mabel Rice at the University of Kansas, someone that I've worked with for a very long time. And this research project focuses on something called specific language impairment in children. Is anyone familiar with that? A little bit? A little bit? Okay, good. So I'm not the expert on this, but I'll give you my sort of layperson definition after listening to Mabel talk about this for a number of years. There are certain children who, for whatever reason, have greater difficulty understanding and applying the rules of grammar. relative to all of their other abilities. So they don't have special impairments, they don't have ID, they just have issues with certain aspects of language. And big questions then is, do they grow out of it? Are the causes genetic or environmental? Those sorts of things. And so to try and get at the latter idea, this is an analysis from a sample of twins. And so they're looking at whether or not in this sample, there's evidence for what's known as a twinning effect. Children who are part of a twin pair seem to have delayed language relative to singletons. And the question, of course, is why. But the whole point of this study, though, was to demonstrate that there is a twinning effect at all. Because previous studies who were focused on the analyses of twins did not give standardized measures that had nationally representative norms, and so they couldn't really tell if the sample as a whole looked different than your average sample of, say, 4-year-olds and 6-year-olds. So this is an example of when we want to compare what we got out of one sample to what we should have gotten from the population mean, just to see if the sample looks different, unexpectedly different. That's the story. Does that make sense so far? Maybe. So these are all a bunch of different standardized tests reported in the paper, where the population mean, because the tests have been scaled this way, is supposed to be 100 with the standard deviation of 15. And the test that I picked for this example is a Peabody Picture Vocabulary Test, which is a measure of vocabulary. And I have ages 4 and 6, and then I have DZ and MZ twins. So DZ twins are fraternal twins, MZ are identical. They share more in common, so you should see a stronger relationship in MZs than DZs. And so what we have here, little n, by the way, sample size per group. We have the mean for the sample, the standard error of that mean, and then I have a 95% confidence interval. And so if we look just at this first result here for DZ twins who are age 4, we thought if there was no twinning effect, this sample's mean should be around 100. Instead, this sample's mean is like 97. Okay, well that's not 100, but like, is that close enough? Well, this is a pretty big sample. This is 771 kids. So that's a pretty big discrepancy. And yeah, the standard error of the mean is 0.6. So we would expect that any one sample of this size would be off from the population mean on average by only 0.6. We're off by like 3. So we're way more standard errors off than what you would expect. So to put that into a couple different terms here, the confidence interval around that mean does not extend up to 100. So I can tell you based on that, because 100 is not inside the interval, we are well into unexpected territory. If we were within expected territory, then 100 should be in here. How unexpected is it, though? We don't know. All we know right now is that it's some kind of unexpected because 100's not in here. So to quantify how unexpected is it, we can do a hypothesis test. So here's the formula again for T. So what we got, the sample mean minus the population mean divided by the standard error, gives us a T of minus 5.48. So minus because we are lower than expected. And that's what we hypothesized in this case. The definition of a twinning effect is a language delay, not a language acceleration. But we could have found either way, so a two-tailed test is appropriate here. Now a T of minus 5.48, that means that our result in terms of our sample mean is 5.5 standard errors below where it's supposed to be. How often, if this sample came from a population with a mean of 100, would we find a sample mean that's 5.5 standard errors away from where it's supposed to be? Less than 0.01% of the time. So this is definitely a reject the null hypothesis. This is unexpected. If this sample of twins came from a population where the mean was 100, we would see a mean this far off like never. almost never. So yes, at age 4, DZ twins show evidence of a twinning effect because they are way lower than expected. Likewise, MZ twins at age 4 show evidence of a twinning effect. DZ twins at age 6, though, other way. So by the time the kids are 6 years old, they've caught up. And actually, in this sample, they've exceeded the mean. So the last column here is tracking the direction of the result. So just saying that something is significant or not is not descriptive enough. The first 2 instances were significant in the expected direction, that they were lower than expected. The third one is significant the other way. And the fourth, the mean being 100.28, 100 is right in that interval, it's not significant at all. So 100.28 is well within expected territory if the true population mean were 100. Okay, how are we doing?
So for this example, is the mean 100 just because of the test norms? Is that where that came from?
That's where that came from. And these are tests that are given to thousands and thousands of children. And so they collect these huge samples of kids, and then they change the way the test is scored to keep it at 100 per age. So it's always the mean is 100. So if you grow like you're supposed to as you get older, you stay at 100. Whether or not there's problems in how they go about norming these tests is a whole separate set of classes. But for this example, mean of 100 is what it's supposed to be. All right, other questions? All right, so I have taken this same data from the table and computed the t-value that goes along with each of these 4 lines. And so the first 2 lines then, what that t is telling us is that our sample mean is 5.5 standard errors and then 6.7 standard errors below where it's supposed to be. So we would reject the null hypothesis. It is very unlikely to find means that low if the true mean were 100. We reject the null hypothesis in the other direction for the 3rd row. And then in the 4th row, we do not reject or retain or just say it's not significantly different than 100. So why we have different results, positive and negative, I don't know. And I'm sure there was part of the discussion in the paper that talked about that, but I am not in charge of writing that section. My job is the results section, and that's about it. So more specifically, the last p-value for this result right here is 0.72. So what that says is that if the true population mean, the null hypothesis, were 100, we would find a sample mean that's this far away from it, like 72% of the time. Super expected territory. That's a technical term. So if I were looking to establish evidence of a twinning effect, meaning that they're lower than they should be, the first 2 results are consistent with that. The 3rd result, even though it's significant, is completely inconsistent with what was expected. So significant is not always good because it could be significant in the wrong direction. But it could still happen, which is why I'm not going to use a one-tail test. The fact that these kids were above average at age 6 happened. So I'm allowing for that possibility by using a two-tailed hypothesis test. All right, so questions on that example before I show you how you can make the software do all this wonderful stuff for you?
I'm just curious how long it took you to do all of that.
Do all the tests?
Like to run the data or whatever you did for this paper.
The hardest part of any analysis is making sure the data set is as it needs to be to do the analysis. That is 80% of my effort. Honestly, this did not take very long at all. Half hour. There are lots of tricks inside software that can allow you to automate things. So just as an example, table 1, if memory serves, had like 8 different outcomes in it. The word phenotype, by the way, in this context means a behavioral outcome that's supposed to have some sort of genetic origin. So I tricked out the software. There is a command in each of these programs that it's by in SAS in particular and by something in STATA, where you can say, hey, can you do the same thing for every separate iteration of this? And so I arranged the data so that the outcomes were all stacked on top of each other. And I said, can you run this 8 times for me? Okay, thanks, bye. And it does. And it spits out the tables, and you can write code to say, hey, can you take this table and export it into Excel for me? Stuff like that. So if you, the nice part about using computer packages like SAS and STATA and R that have a programming language underneath them is that you can automate these sorts of tasks. It's harder to do that in other sorts of packages that are easier to use. So not very hard. Here's how I did it. My mind is blown. Hey, good. I'm happy. I think that's a compliment, right? Or a good thing? Okay, yeah, and maybe not a compliment, but you did once call me palatable. So that's a good compliment for a stats instructor. That's about the best you can hope for. She didn't suck that much today. Aces. But yeah, it's actually not that bad. So I'm going to show you, this is from example 1. Your first homework will give you a chance to practice doing this. And so this is not Mabel's data, but this is the data from example 1. So I'll show you in SAS and then I'll show you in STATA. So this variable is years of education, and I have proc t-test. So that's what we'll use to do a hypothesis test that compares a sample mean to an expected population mean. You would only do this in life in situations in which you have a known population mean to compare it to. So that may not happen in a lot of circumstances, but it's a good way to introduce the concepts, I think. So proc t-test, in SAS, you have to tell it what data set you're using. So when you do this for your homework, make sure you don't have example 1 in there. You would want to change it to homework 1 or whatever your data set's going to be called. HO, can you guess what that stands for?
Hypothesis test.
More specific than that, which hypothesis? Starts with an N.
Null hypothesis.
Yeah, HO is the null. It's not always 0. It's what you expect. So this information right here, this would change based on the context of what you're doing. So for an example, because this is years of education, I picked a value of 12 years, meaning I expect that the mean years of education is a high school degree in this sample. I just picked that to make this example with. In your homework, I'm going to give you an instruction as to what that should be. So you'll look at the instructions and change the value accordingly. Sides equals 2 is whether you want to do a real analysis or some voodoo. So voodoo would be sides equals 1, of course. Alpha is the line in the sand for building a confidence interval. So alpha is the proportion of time that would be unexpected. So 5% is your standard. That's what it will be throughout this class, but that's something you can change if you want. Confidence intervals, I'm trying to remember what that one does. Oh, it's for the standard deviation. It's, see, by the way, do you see the green text up here? The green text is a comment. So this is me leaving notes to myself about what this stuff does, because I don't have this memorized either. So when you learn something new in terms of a routine, I would highly recommend just jotting down what the options do so that you don't have to look it back up later. So this sets a confidence interval around the standard deviation in case you wanted to report that. And you can ask for pictures, but they clog up the output if you don't want them, so I put plots equals none. Var stands for variable. So this would be the name of the column that you're asking for the hypothesis test about. So you have to get the name exactly right. It's not case sensitive, but it does need to be spelled correctly. Otherwise, it will be like, I don't know what you're talking about. And then run closes the command. So anytime you have a proc something, you need to run something to finish it off. Okay, questions on any of that syntax? Okay, so then in the output, you get these three boxes. So big N in SAS, sample size. So 734 people in this analysis. The mean of education is 13.8. So on average, people reported 13.8 years of education. So a little bit of college, I guess. Standard deviation, on average, any one person is off from that sample mean by 2.9 years. So standard deviation describes the spread or the dispersion within the sample. Now, how much wiggle across samples would we expect in that sample mean? That's standard error. So at this very large sample size, the standard error is going to be kind of small. So what this 0.1 is telling us is that on average, any one sample's mean is going to be off from the population mean by 0.11. So a very narrow region of inconsistency. So I'm putting that into notation over here. It gives me the minimum and the maximum, which is nice to know, but not relevant for our hypothesis test. It gives me a confidence interval. So note that I've got two of those here. So the second box here, the first three values are about the mean. So the sample mean is 13.8. The confidence interval or confidence limit, that's what it's either CI or CL across programs. It's telling me the range in which I would expect the population mean to fall 95% of the time. Then I have the same thing for a standard deviation. So just as we would expect different samples to have different means, we would expect different samples to have different standard deviations. So same principle. You could do a hypothesis test about whether your standard deviation is different than expected. So standard deviation of 2.9, here's my confidence limits around that. And then last but not least, the answer. So 733 degrees of freedom is because we started out with 734, but we spent one to get the mean. So there's only 733 more pieces of information that could be used to describe this data. So think of it as like points or money, something like that. T then is 16.87. Now where did that number come from? It came from what we got for our sample mean, 13.8, minus what we were supposed to have as the null hypothesis of 12, divided by the standard error. So yeah, a T of 16. That means we are like 17 standard errors away from 12. So if this sample came from a population where the true mean was 12, we would get a result this far away, not very often, almost never. And so in conclusion, I would say that our sample mean is significantly greater than 12. Greater because 13 is more than 12, and significantly because of the results of this t-test. It would happen less than 5% of the time. It is significant. It is reject the null hypothesis. It is unexpected. Okay, with me? Okay. STATA folks, the output is not as pretty, but it contains the same information. So the command in STATA is also t-test. STATA is case sensitive, by the way. It wants you to type everything in lowercase. The variable that we are doing the t-test on is education, so it's called EDUC in the data set. Equal equal is not a typo. Equal equal in STATA language is setting an equivalency. So in this context, it is testing 12 as the null hypothesis. So 12 goes here on this slide for the same reason 12 went here in the SAS code. You're giving it the benchmark for what expected is supposed to be. What is your null hypothesis? It's 12. In STATA code, commas are used to set off options. And so level 95, can you guess what that corresponds to?
The alpha level.
Close.
Uh,
Close. It's the other one.
the significance. No. Oh,
Right idea, but it's the other side of it, right? Because alpha is
uh,
0.05, right?
yeah, but I
So
don't know what to call it. I forgot.
confidence level.
Confidence.
Confidence. Yeah.
Yeah. So confidence interval or confidence level, you'll see it phrased in that. So like in SAS output, for instance, it's CL because these are the limits of the interval. But yeah, so alpha of 0.05 corresponds to level 95 in STATA. So it's 6 of one, half dozen of the other. Are you defining your area that expected is? That's 95. Or are you defining your area where unexpected is? That's 0.05. Why they can't be the same? If they made them all the same, I would not have a job. If the software were easy and the results transparent, I would be out of a job. So t-test then, the results here, obs is where n would be, number of observations. Here's our mean, here's our standard error, here's our standard deviation. So it's the same information that's provided in the SAS output, albeit with a different ordering of the columns. So you just have to make sure you read to look where you're at here. Here's our t-test, so the 16.8 in our degrees of freedom. And down below right here are the results of 3 different tests based on whether it's one tail one way, one tail the other, or 2. So if your alternative is that the mean is less than 12, so a one-tailed test on the lower side, that can't happen because your mean is above 12. Over here is greater than 12, so that's a one-tailed test. What we want is the one that's in the middle, where exclamation point means not. So we're not calling our shot. We're saying it's not 12. I don't know what it is, but it ain't 12. That's your alternative hypothesis. And so STATA gives you the p-value to 4 significant digits. It's not 0. It's 0 to 4 digits. So the way that you would report this is less than 0.001. So you would never write in a paper that you have a p of 0. That can't happen. It's always less than some tiny number. And then down here is how I would get a confidence interval around the variance. And so that's actually a separate command, but since it's included in the SAS command, I wanted to show you how to do that. So this is the kind of thing I'm going to ask you to give a shot at. So to recap what you would need to change to make this work, the name of the variable and the HO for the value it's being compared to for the population mean. In SAS, you also need to point it to the right data set. So name of the variable, where to go? Right here. Value you're comparing it against is the null hypothesis, and name the data set. All right, so that's that. Questions? Yes, sir. Fayaz.
So looking at the STATA output, I noticed that it's really text-based and like really like no formatting at all. So how do we import this into like a PDF or LaTeX or a Word document?
There are, so STATA is like R in that people write their own routines to do things and you can download them and use them in STATA. I found, for example, a way to turn STATA output into HTML to build my website. So you just have to ask the internet, like ask the Google, how do I make bring STATA code into a Word document or something? And there are probably ways people have made to make the formatting prettier. But this is what it's going to look like when the output spits out for you. It's all text-based. Like
Yeah, I
this.
think the SAS output looks much better, and it's like it will probably be easier to import, I guess.
Yes and no. So a little bit about the SAS outputs. It wasn't until version 9 that they started doing this HTML output as a default. I actually hate it when I'm building handouts because it's impossible to work with. Because each of these is objects and they like move all over the page. People are talking smack in the chat window here. So when I build handouts with SAS output, I actually get the old version that looks like this because I can annotate this much more easily and work with it. Incidentally, in SAS, there's an option in the results to change the HTML style. So kind of like what's known as a cascading style sheet in HTML to where you can color it up. Like you can change it to where this is like red and black or blue and green, or like they have different color schemes. So if you don't like blue, you can change it. So that's just one fun thing about that. But yeah, I'm sure there are analogous ways to do that in Stata. I've never really bothered other than just turning it into HTML to build the Piles of Variance website.
So yeah, I'm sorry if I'm wasting the time, but like, so with HTML, the thing is that, so I turned in a paper last, I think, yeah, last towards the end of last semester, and so I could do it in HTML because HTML allows so much customization, and you can, you can make the graphs interactive. If you click on them, you can see the values with R. But my professor, who I turned it to, said that you need to submit like a PDF or a Word document, something that I can print out, and so yeah.
That will be true anytime you submit a manuscript. Some publishers will take like a LaTeX file directly, but most of them want some kind of Word document that they can have internally. So unfortunately, you're going to have to, like, that's going to be how it's going to be. So, for better or worse. But yeah. All right. How are we doing on time? We're doing good, actually. I think we might actually finish most of this today, and then we can start something new next time. So, what about binary variables? So, same ideas apply with a little bit of additional complication because of the way that binary variables behave. So this, by the way, none of this is on your first homework. So we've just now finished everything that you need to do your first homework, which means I will be able to put it up hopefully during office hours today. I'll send you an email when it's available so that you can start working on it, although it's not due for 2 weeks. So I just, in terms of homework, the hardest part of this homework will be getting SAS or Stata to find where you put the data set to be able to do the analyses. Just getting used to using the virtual desktop and the idiosyncrasies of that, that is the hardest part of that. So if you get stuck on that part of the process, please let me know. You can come to office hours and share your screen and I can help you troubleshoot any of those things. Once you get to the point where it can find your data set, you're home free because from there it's going to be just fine. So this is all sort of extra material relative to that. So in a binary variable, so a type of categorical variable where there's only two options, the mean is what's labeled as P here, the proportion of values that have a 1, and Q is the proportion of values that have a 0. So the same principles hold in terms of what makes a sample mean more inconsistent, more variability, and less sample size. But variability is tied to the mean in binary data. It's not a separate thing. Once you know the mean, you know the variance. So that means that how we describe the variability in sample means for binary variables has to work a little bit differently. So just to illustrate, I once again played God. I simulated 100,000 fake people, and I did so for one variable that has a mean of 0.6. So 60% of the cases have a 1, 40% have a 0. And then I made a variable that has a mean of only 0.2. So this is sort of a more skewed variable where the proportion of ones is much less frequent. And by the way, the distribution that goes along with this is known as Bernoulli. It's capitalized because it's somebody's last name. If you have a binary variable that has more than one trial, so like if you roll the dice 6 times kind of thing, or you can get it, or coin flip, let's go with that. Like if you did 6 coin flips, that would be a binomial distribution. You may have heard of that in some of your other courses. And so Bernoulli is a special case of binomial when there's only 2. So just a little more, not everything in the world is normal. There's plenty of other types of shapes that variables can take on. So I did the same repeated sampling experiment that I described for our quantitative example. So within each of these, starting with the one that's 0.6, I grabbed samples of 5 people 1,000 times, samples of 10 people 1,000 times. And here's the distribution of the sample means. So it's a little noisier. There's some holes in it because if you only have 5 people, there's only certain values that the mean can possibly be. But as you get more people, the mean gets closer to looking like something like a normal distribution or a t-distribution, meaning it's symmetric, it has a peak in the middle. And so the more people, the better it behaves in terms of approximating something that looks like normal and the less noise there is. So the standard deviation of these pictures here decreases as you get more people. If we have the other variable though, so the one where the mean was only 0.2, these don't look normal. Like this one, how would you describe this one?
Positive skew?
Yeah, positive skew because the tail is heading in that way. And yes, Bernoulli totally does sound like a pasta. I concur. But yeah, this thing ain't normal. And so it takes more people to get to something that loses that skewness to it because the mean is causing the skewness. And so the teeth idea doesn't work as well, or I say the Z idea doesn't work as well in small samples. For whatever reason, they don't use T in this case. So if you're interested in testing the mean of a binary variable against a hypothesized population mean, recommendations based on the relevant literature says that in order to use a Z to do that, you should have the number of people times the proportion of ones be greater than 5 or greater than 10, depending on what textbook you look at. And so I used a normal approximation in the examples I'm going to show you because the way that each program handles this is a little bit different. For whatever reason, they don't use T for binary variables, but people have come up with other sorts of corrections or hacks, as you might call it, to try and get a better way to test a sample mean against a population mean for binary variables, particularly when you have small samples. And so this is something that I don't have time to cover a lot about in this class, but if anyone is interested, I can direct you towards some extra readings to talk about categorical data. So generally speaking, if you're interested in testing hypotheses or answering questions about binary variables, ordinal variables, nominal variables, that's known as categorical data. And so there's different procedures that have to be used because the variance and the mean are tied together in those instances in a way that they're not for quantitative variables most of the time. So I've linked to some extra sources on how to do that as well. But the same process in terms of the procedures operates. You can get SAS or STATA to do the heavy lifting. So this isn't something I'm going to ask you to do, but I wanted to show it to you in case you needed to do it in your life. So to test the mean of a binary variable from a sample against an expected population mean, you can do that in proc-freq. So just to recall, proc-freq stands for frequencies. It's how you get frequencies and percentages for any categorical variable, and you can also do some hypothesis tests with it. So for instance, the variable that I am using right here is called less high school. It is coded so that a 1 means somebody has less than a high school degree, and a 0 means that they have more. And so I'm testing it against an expected population mean of 0.1 in this case. So here is the summary of the frequencies of each category, the percent of each category, and the cumulative versions of those. It also gives me a standard error for that proportion of a 0.12 confidence intervals, and it gives me a Z. And so here's where those numbers came from. So if I were trying to say whether or not my sample proportion of 12% of my people having less than a high school degree is different than the expected 10%, the result of that corresponds to a test statistic of 2.2. So my mean of 0.12 is a little over 2 standard errors above the population mean of 0.1 that I thought it would be. And that would happen about 3% of the time if my sample came from the population I thought it did. So this would be a significant result because 3% is less than my alpha level of 0.05. So we're in the tails, unexpected territory for this. In STATA, It's the command PR test, so it looks very much like t-test, except it's proportion test, as they call it. The name of the variable, the null hypothesis, and your alpha level for building your confidence intervals and such. And then you get 3 hypothesis tests here. The one in the middle is the two-tailed test, so not equal to 0.1, and there's your same p-value of 0.03 for that, with the same conclusion. I wanted to show you how to do the other side, because what the software tests by default is STATA will only test the proportion of 1 values, which means that if you're interested in testing the proportion of zeros, you have to recode the data. So I wanted to show you just an example of what that would look like. In SAS, I recoded the data into the opposite meaning. So I have another variable called grad high school, where 1 means you graduated high school, and I can test that against a proportion of 90.9. And so I get the exact same result in the opposite direction, meaning that I have fewer people than expected because it's 87% relative to 0.9, which is the same thing that we just found from the opposite perspective. I had 12 relative to 0.1. So just to say that you kind of have to dig into the documentation sometimes to figure out exactly what you're allowed to test. ProcFreak allows you to specify whether you want to test against the zero, the proportion of zeros, or the proportion of ones. STATA only lets you do the proportion of ones. So I wanted to throw that in there as well. All right, time to pause and reload. How are we doing? Okay so far? All right, then just a little bit left here. One thing I want to point out, this idea that there is a ready-made formula for how to get the standard error of the mean or the standard error of anything is not always going to be the case. So what I'm describing is the use of asymptotic sampling distributions. Asymptotic means what would happen if we had an infinite sample size. So as n gets bigger, things get more well behaved. So all of the off-the-shelf formulas that people use to provide standard errors have this sort of asymptotic belief structure put in. But that begs the question, okay, what if you can't rely on asymptotics? And what if you don't have a ready-made formula? There are other ways to get standard errors that you may come across. And in fact, in other versions of this class, people teach that instead. So like in 4143, Brandon LeBeau talks about this. He does bootstrapping as a way to get standard errors, for instance. But it's the idea of resampling. So one way to get a standard error, for instance, using just one sample, is to pull repeated samples out of it with replacement or without replacement. And you can end up then pooling across those repeated samples from your one sample, figuring out what the distribution of the sample mean would look like, and then figure out what the average distance from that is. So I want to just point you towards this as a point of reference in your head. These words, bootstrapping, jackknifing, permutation tests, and Markov chain Monte Carlo, all rely on this sort of resampling way of getting standard errors. And so in chapter 18 of one of the books, they go into this. That's on your syllabus. So again, I don't have time to talk about that, but I just want to mention that there is this whole other way of getting standard errors. But once you get the standard errors, you do the same sort of process. Build a test statistic, figure out how many standard errors away from the null hypothesis you are, and then you get your p-value and make your conclusion. So the process works kind of the same way. All right, so wrapping up then, salient characteristics of variables, central tendency, and dispersion. So we worry about the mean most of the time, median and mode if we have a skewed distribution where the mean would be pulled towards one of the tails. For dispersion, we usually talk about that in terms of standard deviation. That squared is variance. We need a standard error to make inferences, and we can make hypothesis tests using those standard errors. I just have a few more things here I wanted to point out. How do you get a standard error for other quantities besides the mean? Just a couple slides on that. For instance, the variance. So the same process for building a standard error for a variance is going to need slightly different distributions. So we talked about this at the beginning of class, right? I think, Jerome, you remembered talking about variances being tested against 0. The smallest that a variance could ever be is 0, right? And so if I had a data set in which all of the cases had a 0 value, it's a constant, not a variable. That actually has a special name that's known as a degenerate distribution, by the way, when you have no more variability. So if the smallest that a number could be is 0, this idea that what the number could be is normally distributed can't work, because half of it is not going to be there, right? You're up against a wall. So people smarter than me have figured out that variance is actually distributed more like a chi-square. So we're going to see chi-square in the next unit, but it is a skewed looking distribution. And so it gets to be more symmetric when you have a larger degrees of freedom. In this case, it's numerator, not denominator. And so the distribution of what a sample variance is relative to a population variance is chi-squared. And that formula gave me a headache trying to explain it, so I went to the Google to try and find some other things, and I found someone else's description of it and stole it. So there's a little YouTube video here linked on the bottom for where I got this. This person did a great job explaining this, and so I wanted to just give you a couple slides. So if I only have 5 people and I have a variance of 1, the sampling distribution would look like this because it's bounded at 0. Variance can't be lower than 0, so what it could possibly be is skewed. As we get a larger sample size, like 20, then it gets to be something that looks more normal. So this same process of what is our sample statistic, how inconsistent would we expect it to be across samples, we can do that for anything, not just a mean. We can do that for a variance. The trick is just knowing how do we describe the expected pattern of inconsistency and whether or not we can find a distribution that maps onto that. This one looks more like chi-square. This one starts to look more like normal when you get enough people. So in practice, you can get a standard error for anything. Sometimes it will be spit out by your software using off-the-shelf asymptotic formulas. Sometimes you might have to work a little harder for it, meaning that you'll have to do some sort of resampling or run in some sort of additional routine. But the idea of a standard error is the way that we make a leap from what we got in one sample to what we could get in a population. That's the key. Standard error is everything. And that's my story, and I'm sticking to it. Okay, questions? So, big picture, all we've done so far is talk about one variable. Summarize that one variable. Central tendency, mean, median, mode, dispersion, standard deviation, variance, stuff like that. Asymmetry, meaning skewness. The next logical thing would be, okay, I have a variable, what do I do with it? Well, I can relate it to other variables. Are things related in the way that I expect them to be? So what we're doing next, which I'll get to start, I'll put the slides up after class here, is bivariate measures of association. So bi means two variables at a time. If I have a variable that's called 1x and another variable called y, how can I tell if they're related? That's where we're headed next. And the trick to that is figuring out what kind of measurement each one has. So if a variable is binary and a variable is, say, nominal, there's a different way of saying whether or not they are associated than if a variable is quantitative. So we'll be doing things like correlations, chi-squares, and those are the main kinds. So this, if you've had stats before, will sound familiar. So we're still within expected territory in terms of that. All right, then I think this is a good place to stop. Nice even break, finishing material. That always feels nice. Any questions or comments before we call it a day? All right, then I am going to put up homework 1 hopefully later today or tomorrow. I will send out an email as soon as that is available. It's not due for 2 weeks though. Formative assessment number 1 is due next week. So the idea of that is that you log into Icon. It's there under assignments, and you get 2 points just for answering the questions. Even if they're wrong answers, that's fine. It's just an opportunity to provide some structured review in between when assignments are due. We will go over the answers as a class the day after it is due. That way, if there's any lingering misconceptions or things like that, we can talk about it. So you can work on that anytime you're ready. Okie dokie. Okay, then let us call it a day. Stay warm, stay safe, and I hope to see you Thursday. Bye, everybody.